Reductones. Reductones are compounds which contain the in alpha diol alpha carbonyl groups. Actually, this will be alpha. This will be alpha. Reductones are compounds which contain the in alpha diol alpha carbonyl group. This is the structure of reductone. Ascorbic acid is not reduced by lithium aluminum hydride. Thus, ascorbic acid does not contain a normal carbonyl group. If it was the normal carbonyl group in case of ascorbic acid, then it should be reduced by lithium aluminum hydride. Actually, all reductones are not reduced by lithium aluminum hydride, and ascorbic acid is also a reductone. This is the structure of reductic acid, which is also a reductone. The reductones means you have a carbonyl group, and in the alpha carbon, the alpha and beta carbons are actually double bonded and they contains two hydroxyl groups. See this is the ketone group. The alpha carbon contains a hydroxyl group and a double bond with the beta carbon, which also contains the hydroxyl group. In case of reductic acid, this is the carbonyl group. This one is the alpha carbon, which is doubly bonded with the beta carbon, and both of this alpha and beta carbon contains hydroxyl group. This is all about reductone. Now come in detail of ascorbic acid, which is known as vitamin C. This is the reduced form of the ascorbic acid, and this is the oxidized form of the ascorbic acid. Vitamin C was called hexuronic acid. The structure of vitamin C was elucidated by Howard Hirst and their co-workers. The molecular formula was shown to be C6H8O6, and since the compound formed a monosodium and monopotassium salt, it was thought that there was a carboxylic group present. Vitamin C behaves as an unsaturated compound and as a strong reducing agent. It also forms phenylhydrazone and gives a violet color with ferric chloride. All this suggests that a ketoenol system is present in vitamin C or the ascorbic acid. The presence of an aldehyde group was excluded by the fact that vitamin C does not give the Schiff reaction when boiled with hydrochloric acid. Ascorbic acid gives a quantitative yield of furfuraldehyde. This is the furfuraldehyde. If you take ascorbic acid and then boil it with hydrochloric acid, you will get this furfuraldehyde. Now this is the synthesis of ascorbic acid, the mechanism of the synthesis. At first take the L-xylose, then make the 2 position as ketone. You know how to do it. You can make it via ozone. Then add KCN CaCl2, so you will get this structure. Actually, this KCN will attack this aldehyde group, and then after hydrolysis you will get this type of acid, which on tautomerism will give this. And after eliminating water, that means when this OH group is actually attacking this carboxylic group and forming a gamma lactone. This is a gamma lactone because this one is the carbonyl group. So this one is the alpha carbon, this one is the beta carbon, this one is the gamma carbon. So this one is a gamma lactone. So at last you will get the structure of ascorbic acid. There is another process which is in use of the synthesis of ascorbic acid, which starts from the D-glucose Then hydrogenases with the presence of copper and chromium, you will get sorbitol. After that, you can use Acidobacter sorbo. I can't see this. What is it? Acidobacter suboxidans. Then use the Acidobacter suboxidans. You will get this structure, which actually after ring closure will give sorbos. Oh ho ho. After the ring closure, it will give the sorbos. So actually, what is happening here? This OH group is attacking this ketone group. So you will get a 5-member ring. See, you can get a 5-member ring, and then add acetone and acid. Then you will get the diacetone sorbos. After that, react it with KMNO4, the basic KMNO4. Then something will happen. And what is it? Actually, this CH2OH will be oxidized, and then add some acid, so you will get 2-ketogulonic acid. 2-ketogulonic acid. Then if you give chloroform in HCl solution, so at last you will get L-ascorbic acid. This one. Just try to understand, do it yourself.